Hello everyone, so in the last video we looked at how to find the area under the graph of y equals x squared from x equals 0 to x equals 1. And now we are going to do basically the same thing but for a general function f of x, and instead of on 0, 1 being on the interval ab. And the steps are going to be mostly the same except that everything, the notation is going to be a little more tricky because we have a general situation. But okay, we can handle it, so let's get started. So let f be a continuous non-negative function on ab, and let S be the region which is bounded by the x-axis and the graph from x equals a to x equals b. So it looks something like this. Depending on what f of x looks like, it could look slightly different. But okay, this is a general picture. And what did we say the steps were? If we remember, we said the steps were to approximate by rectangles in a very systematic way. So we approximate by n right rectangles, meaning that we divide AB up into n equal subintervals, all of the same length. Those are going to be the bases of our rectangles. And then over each of those subintervals, we draw a rectangle whose height is the value of our function at the right endpoint. This gives a bunch of rectangles. We add up their areas by doing base times height. If we add up those areas, we get an estimate for the area under the curve. The more rectangles we take, so the higher n it is, the better and better the approximation we get. And in the end, if we let n go to infinity, so the number of rectangles goes to infinity, we get the true area. So those are the steps that we want to replicate in a formula so that we can actually compute things. So let's go ahead and do that. So our first step, we divide AB into n equal subintervals, or n subintervals of equal width. So AB has length b minus a, right? If we want to find the length of an interval, we just subtract the endpoints. So the length of AB is b minus a. If we want to divide that into n equal subintervals or n equal pieces, we just divide by n. So the width is b minus a divided by n. And then since we want to, so these are going to give the base of our rectangles. So then since we want to define the height of our rectangles, remember the height of the rectangle of each rectangle is going to be the value of the function at the right endpoint of the subinterval. So since we're going to use the endpoints of the subintervals, we need to give those things names and a formula. So how do we understand the endpoints of the subintervals? So let's think if we start on the left, we start over at A. Starting at A, we have a subinterval of width delta x. So it's going to go from A. So if it starts at A and it has length delta x, we're going to go from A to A plus delta x. And then the next subinterval is going to start at a plus delta x, and it's going to have length delta x. So we go from a plus delta x to a plus 2 delta x. And then the next one will go from a plus 2 delta x to a plus 3 delta x, and so on. So we can understand what those endpoints of these subintervals are going to be. We just start at a, and each time to get the next endpoint, we add on delta x. Okay, so let's have a formula for that. So here are the subintervals. The endpoints are x0, x1, x2, and so on up to xn. So the xi are the different x's are the endpoints of our subintervals. And xi is a plus I times delta x. So this looks confusing, but this is basically what we just said about getting the endpoints. Right, we start at a, and then we go from a to a plus delta x. Then we go to a plus 2 delta x to a plus 3 delta x. Because the length of each subinterval is just delta x, we add on delta x each time to get the next endpoint. Okay, so to summarize, we managed to give a notation to the endpoints of our intervals. So they're xi with xi following this formula. And all of the subintervals have the same length. All the base of the rectangles have the same length. That's delta x equals b minus a over n. Okay, and then lastly, we need to understand the height of the rectangles. So we said that over each subinterval, we want to approximate the region by a rectangle whose height is the value of the function at the right endpoint. So here over the subinterval xi minus 1 to xi, which is general, depending on I, this is a general subinterval. Over that subinterval, we approximate by a graph, by a rectangle, whose height is the value of the function at the right endpoint xi. Or in other words, we approximate by a rectangle whose height is f of xi. Okay, so to summarize, we divided AB up into a bunch of smaller subintervals, xi minus 1 to xi. Each of these has the same width, delta x, but we approximate by a rectangle who has height f of xi. So we have a bunch of rectangles, heights are f of xi, widths are delta x. We multiply them together to get the area of the ith rectangle, and then we add up all the areas of the different rectangles. So if we do that, we should get this formula Rn, which is the estimate if we approximate by n right rectangles. So starting from the first one, on the first interval, x0 to x1, the height is f of x1, the width is delta x, so the area is f of x1 times delta x. Going on to the next one, x1 to x2, the width is delta x, the height is f of x2, so we get f of x2 times delta x. Okay, and then we have a bunch of terms in the middle. And then on the last rectangle, the width is delta x, width is always the same, and the height of the rectangle is the value of the function at the right endpoint, which is f of xn. So this is our general formula for the right rectangle approximation with n rectangles. So, if you're asked to approximate by 4 right rectangles or 6 right rectangles or whatever, you could draw the same picture, play the same game, or you could just use this formula. Okay, so this brings us to the area. We said to go from these estimates to the true area, we have to take a limit as n goes to infinity. So that's all we're saying here. If we want to get the area of the region under the graph from x equals a to x equals b, we do this right rectangle approximation with n rectangles, and we'll let the number of rectangles go to infinity. So if we remember back to the last video, we did this with y equals x squared. We got some kind of formula involving n, involving the number of rectangles. And then as n tend to infinity, we get rid of the n and it goes to 1/3, which was the area. Okay, so we already did this in that very simple example. It's just the same thing, but with a more general function, more general interval. Okay, so next up, there are a couple of variants that we need to understand. So as we said, here we use n right rectangles. We could equivalently use n left rectangles. So what would change? Remember back to y equals x squared, if we used 4 right rectangles or 4 left rectangles, we got different estimates. One was an overestimate, one was an underestimate, but they were different numbers. The approximations with left rectangles and the approximations with right rectangles will be different. But when we take the limit, we get the same thing. So we get the same thing after taking the limit. So the area is going to be the same in either case. So it doesn't matter if when we do approximations, left rectangles and right rectangles are just as good in approximating as each other. If we take the limit, we get the true area in either case. So you don't have to do both. You can just pick one and do one. Once you compute the limit, you'll get the true area. Notice the slight difference with left rectangles is that the values of the function we use are shifted. So we don't use all the values of the function in each case. So why is that? If we think back to what our rectangles represent, so the first rectangle is over x0 to x1. And with right rectangles, we use the value of the function at x1, whereas with left rectangles, we use the value of the function at the left endpoint. So x0 to x1, the value at the left endpoint is f of x0, and then we multiply by delta x. The second rectangle, which is x1 to x2, if we're using right rectangles, we use f of x2. If we're using left rectangles, we use the value at the left endpoint, which is f of x1. And so on and so on, going to the last one, which is xn minus 1 to xn. With n right rectangles, we use the value of the function at the right endpoint, which is xn. With left rectangles, we use the value at the left endpoint, which is f of xn minus 1. So be careful if you're using left or right rectangles and finding approximations and things like that. Don't use all of the heights, right? On right rectangles, you're going to use all of the heights except the one on the left. With left rectangles, you're going to use all of the heights except the one on the right. So do be careful. That's a common mistake that people make. Okay, and then here are a couple more variants. So there's nothing special about left endpoints or right endpoints. We could use some intermediate point. We could use, say, the midway point. If on an interval, you want to approximate the graph by a rectangle, maybe the thing that could make the most sense would be to approximate by the area on the center. So we could take the midpoint of the rectangle, use the height of the function at that point. Maybe we could even do something else. We could use the largest value of the function or the smallest value of the function and so on. But okay, in general, we have these sample points. So xi star is just any point inside xi minus 1 to xi. In different approximations, we can choose the xi star. The only thing it has to satisfy is that it's somewhere inside xi minus 1 to xi. So we get to choose those. That's why they're called sample points. And okay, the approximations we get without taking the limit are going to be different. But when we take the limit, whatever sample points we take, when we take the limit, we should still get the same true area. Okay, so here is a very crude picture, I'm sorry, of sample points. So we divide AB up into n equal subintervals of equal length. So we see x0 to x1, x1 to x2. In the middle, representing a general interval, we have xi minus 1 to xi, and so on. And then inside each of those intervals, we pick a sample point. So in the first interval, which goes from x0 to x1, we pick x1 star. In the second interval, x1 to x2, we pick x2 star and so on. And then rather than using the value of the function at the left endpoint or the right endpoint, we use the value of the function at the sample point. Okay, so here the height of the rectangle is the value, or should be close to the value at f of x1 star. On the second one, we use the value at x2 star, so we are using the height f of x2 star, and so on and so on. So these are sample points. And okay, if we pick different sample points, we get different approximations. So if we use, as we said, if we place all the sample points on the left, we will get left rectangle approximation. If we place them all on the right, we will get right rectangle approximation, which we've already seen. However, there are these things called upper sums and lower sums. Upper sums mean that on each subinterval, we use the largest possible value of the function so that we get a rectangle which lies above the curve. And with lower sums, we choose the sample points where we get the lowest possible value of the function. So we get rectangles which lie underneath the curve. So these are really good for getting upper estimates and lower estimates of the area. Okay, so here, let me try to represent that on a picture. So here I drew 4 rectangles using upper sums and lower sums. So here, for instance, with the first rectangle, we use the value of the function at the largest point, which is somewhere around here, plus or minus my drawing errors. On the second one, we use the value of the function at we use the largest possible value of the function, which is up here. Third one, we use our sample point to be where the largest value is, which is up here. Last one, we use our sample point to be on the right where there is the largest value of the function. So this will be an upper sum. So notice with upper sums, it's not always the left or the right. It could be sometimes the left, it could be sometimes the right, it could be somewhere in the middle. You just want to choose the point where the function has the largest value. And similarly with the lower sums, right? So here is a lower sum. With the first subinterval, the smallest value of the function is on the very left, so we choose that as our sample point. The second one, the smallest value of the function is on the very right, so we use that one. Third one, and so on and so on. We always choose the sample point where the function has its smallest possible value. So these are upper sums and these are lower sums. Okay, so we're probably sick of writing out these big, long, complicated sums by now, so it would be nice if we had a way to write sums more simply, and we do, but we need to understand something called sigma notation. So to represent sums that are going to have many terms, we use this thing called sigma notation. So what is the meaning here? So here, this Greek letter, which kind of looks strange, this one, is the Greek letter called sigma, and it means to sum. Normally it means to sum things, or at least in mathematics, if you see sigma, then it means you're probably going to sum things. So what are we summing? Okay, the things that we're summing are AI, which are these terms appearing here on the right. Okay, so we are summing these things called AI. Here I is the index. So to get different things, to get the different terms in the sum, we replace I by different numbers. So we get all the terms in the sum by taking AI and replacing I by m plus 1, m plus 2, up to n, and so on. So here m tells us what the first term is, and n tells us what the last term is. So AI are the things we're summing. We get the different terms by plugging in I equals m, I equals n plus 1, I equals n plus 2, and so on, up until we get to I equals n. Okay, so here are a couple of examples. For instance, the sum, or sigma. So sometimes I'll say sigma, sometimes I'll say sum. The sum from I equal 1 to 4 of I. Okay, what are we doing? So sigma means, okay, I have to sum something. I equals 1 tells me I'm starting at 1, and the 4 up here tells me I'm going up to 4. And the thing I'm summing is I. And we said we get the different terms by replacing I first by 1, then by the next one, then by the next one, and so on. So we replace I first by 1, we get 1. Then we replace I by 2, we get 2. Replace I by the next number along, we get 3. By the next number along, we get 4. Okay, and then 4 was the last term, so we should stop. So in the end, we get 10. Okay, going on, the sum, or sigma, from I equals 3 to 6 of 2i. So we get the first term by subbing in I equals 3. We get the second term by subbing in I equals 4. Then sub in I equals 5. Then sub in I equals 6. And then, okay, I equals 6 was the last term, so I should stop. And then if you multiply these out and add them, you'll get 18. Okay, next up, the sum from I equal minus 2 to 2 of I squared. So we get the first term by taking our formula I squared and replacing I by minus 2. Then we move up 1, we go to minus 1, we sub in minus 1, then we sub in 0, then we sub in 1, then we sub in 2. Okay, but 2 is our final term, so we are going to stop there. So we get whatever this is. So if we have something in sigma notation, AI is the general term. We can write out the sum as a more traditional sum that we can actually maybe calculate by replacing I first by m, then by m plus 1, and then adding 1 each time, and then up until the last time when we sub in I equals n. Okay, so how can we use this? Well, these big, long, complicated sums. So here is the sum we had with sample points. So this was the area approximation we get if we use sample points xi star. And we can write this in this much shorter way as a sum in sigma notation. So let's just check that we actually get that these are actually equal. So here we are summing something, and the first term is going to be when I equals 1. So that we get the first term by subbing in I equals 1 here. If we do that, we get f of x1 star times delta x, which is, okay, the first term. The next term, we are going to sub in I equals 2. So we get f of x2 star delta x, which is exactly what we have. And then we keep summing until we get to I equals n. So if we sub in I equals n, we get f of xn star times delta x. Oops, I made a typo here, should be f of xn star delta x, sorry. Okay, so, and then finally we can write more briefly. Now that we have a way of writing these complicated sums in a more short way, we can write the formula for the area. So we say the area is the limit of the rectangle approximations, whether we use left rectangles or right rectangles or sample points or whatever. So here was with the sample point approximation, so the area is just the limit. And okay, we are free to choose. If you're just trying to calculate something in an example, make your life easy, and probably right endpoints will be the simplest thing. You could use xi star equals xi for right endpoints. Sub that in this formula. You get a as the limit of the sum from I equal 1 to n of f of xi times delta x. Okay, so we're going to be talking much more about this when we do integration. But yeah, so we said the strategy was pretty much the same as with y equals x squared from 0 to 1. We chop our interval AB up into n equal subintervals. The endpoints of those subintervals are xi. They all had weights delta x equals b minus a divided by n. Of each of those subintervals, xi minus 1 to xi, we approximate by a rectangle. And the rectangle can have different heights depending on what we choose. So if we want to have, say, right rectangles, then xi minus 1 to xi will have height f of xi. If we choose left rectangles, it would have height f of xi minus 1. If we choose sample points, it would have height f of xi star, which is some point in the middle. You could have upper sums where we choose the largest value of the function, lower sums where we have the smallest. But in the end, okay, the story is the same. We have n rectangles. They have a base, b minus delta x is b minus a over n. They have a height, which we just figured out. We add up their areas. This gives us an estimate for the area. And then when we take the limit, whatever we choose, when we take the limit, we always get the same value, which is the true area. And finally, we looked at this thing called sigma notation, which is a way to briefly or more easily write these complicated sums. Okay, so don't worry if this seemed a little complicated. We'll talk more about it soon. This is probably the most complicated piece of notation we'll have in the course. So once we get our way around it, we'll be well on our way to the end of the course and understanding everything. Thanks, everyone. See you next time.